Okay, hello everyone in the video. So we have reached part 3 of chapter 5, which is basically chapters 5 and 6 together. Okay, so previously what we have done is that we have discussed the tension force in section 4, and we have done a direct application, which is application number 2, that stresses the different properties and why the tension force exists. Now we will do the same analysis but for another force, which is the normal reaction. So let me here write section number 5, which is given by the normal reaction and so the normal reaction and to do so, let me consider the following problem in which we have a table and on this table we will place a solid S, let's say for example having the shape of the cube, and for sure that this solid has a mass. So this is the solid S and this is the table. And because we are going to discuss forces, let me consider the following 2 points. So we are always interested first at the center of gravity of the solid, so this is the center G. Okay, so previously what we have done for the tension force, we has that said S is under the action of its weight W because it has a mass. Then here let's write a similar statement which is given by S is under the action of its weight W since it has a mass. Now let me represent the vector W, which is acting vertically downward, and because W is classified as an acting at a distance, then it will have a point of application which is the center of gravity G. Okay, so we said that also then we expect that S must fall down due to the action of the weight W. So let me also write that then S, then we expect that S just 1 second will fall down due to the action of the weight. But actually here, so this is the weight. S is not falling. What is preventing S from falling is the table. But we need to explain this. At the level of the forces. Okay, so we will introduce a new force called the normal reaction. So here, because so how we need to explain this at the level of the forces. In order to oppose the action of the weight, we will introduce a new force called the normal reaction. So the normal reaction N is the force exerted by the support, and here by the support I mean the table, on S. Okay, so in order to explain why S is not falling, I have introduced a new force called the normal reaction. So the normal reaction is the force responsible to balance the effect of the weight. So if the weight is acting vertically downward, the normal reaction will be acting vertically upward. So in order to study the properties of this force, first of all we need to classify this force, as we have done in the case of the tension. So let's start by the classification. Let me write down here the classification. So by the classification, we need to mention whether N is a contact force or acting at a distance. Recall that the only three forces that act at a distance are the weight, the electric, the magnetic. All other forces are classified as contact forces, in particular the normal reaction N. So N is classified as a contact force. What are the properties of N? So properties of N. And by the properties here we mean the point of application, the line of action, the direction, and the magnitude. So let me say point of application, line of action, the direction, followed by the magnitude. Recall that whenever we are listing these properties, we need to list them in the following order that is given by the builder. Now, because it's classified as a contact force, then the point of application will be the point of contact. Now, what is the point of contact? The point of contact is the point which is the connection between the two bodies that are at interaction. The solid S being placed on the table, so they have several points that are in contact, and they are given by this point, this point, this point. All of these points are the points of contact, but we'll consider only one point, which is this point. So let me consider in blue this point, and let me give it the name A. So in this case, A is being the point of contact between the S and the table. Now notice that if we want to place A exactly, A will be vertically downward, aligned with the point G. So this is the point A, which is here. But now in order to represent the normal reaction properly and to represent it in a proper manner, so I have shifted A bit to the right. We could have shifted A bit to the left, but I will consider the right shift just in order whenever we need to represent N, the representation will be clear and we will differentiate between N and W. Okay, notice that in the case of the tension we didn't do so because the point G was down and the point A was up, but in this case A is down and G is at the top. So just in order to represent these vectors properly, I have shifted a bit to the right. So this is the point of contact A. So what about the line of action? The line of action is given by perpendicular to the support. And if you refer back to the figure, what is perpendicular to the support? This is perpendicular to the support, which is like this. Okay. Now what about the direction? Notice that N must balance the effect of W. For this reason, it must be upward and not downward. Whether if it's downward, then it will completely fall down. But we need to be balanced. So perpendicular to the support in this case, this is the perpendicular, and by perpendicular here in this case, this is given by vertical, and it is acting upward. As for the magnitude, I will leave it as an empty box because this depends on the problem itself. Now here, the properties that are always fixed are given by the point of application, which is the point of contact, the line of action, which is perpendicular to the support. The one that I will place now in a box, it changes from problem to problem. So these that I have placed in a box, they will change depending on the problem that you are referring to, okay? Whereas everything left that I didn't place in the box will be fixed as a main property for the normal reaction, okay? So, and as you can notice that the arguments based on which we have deduced or introduced this force are very similar in the case of the tension, okay? Now let's do application number 3. Or first let me consider the following note, that whenever we have a mass, we will have a weight. Whenever we have a string or spring, we will have a tension force. Whenever we have a support, by the support I mean a table, we have the normal reaction. Here by the weight we are talking about the W vector, by the tension we are talking about T vector, by the normal reaction we are talking about N vector. And we don't forget these vectors on these quantities. Now let's consider application number 3 as a direct example on what we have just said. And let me say a solid S of mass M is equal to 250 grams placed on a table. Take G is equal to 10 newtons per kilogram. And recall that from the previous video we have discussed that the value of G reflects the planet on which we are performing this experiment, okay? So if we are performing this experiment on the surface of Earth, we expect that the value of G is 10. If we are performing this experiment on the surface of the Moon, then the value of G, for example, is given by 1.67 Newton per kilogram. Let me consider this table. This is the solid S placed on the table. This is the point G, which is the center of gravity of S, and this is the point A, or let me say this is the point M, which is the point of contact between the solid and the table T. Let me say that this is the table T. And now let me pose the following questions and say, number 1, what are the forces acting on S? Number 2, classify these forces as acting at a distance or contact force. Number 3, list the properties of the above forces. Number 4, represent the above forces using a scale. 1 centimeter corresponds to 1.25 newtons. And let's start. Now, what are the forces acting on us? As usual, because this object has a mass, then it will be directly subjected to the weight W. And in this case, if we refer back to this note, whenever we have a support, and the support may be a table, then we have the normal reaction and now in number 2, we need to classify these forces as acting at a distance or contact force. Now, we know that the weight, the electric, the magnetic are the only 3 forces that act at a distance, so W is acting at a distance. Whereas the normal reaction N is not weight, nor electric, nor magnetic, so it's classified as a contact force. Now in number 3, they are telling me list the properties of the above forces. So by the above forces we mean the weight and N. So let me start by the properties of W. Now the properties are given by the point of application. Line of action, direction, and the magnitude. Now the 3 properties that will not change are given by the center of gravity G, the line of action is vertical, and the direction is downward. Here, let me add also, knowing that they have the same magnitude. Okay, so this part that I have just added is for part 3. Now regarding the magnitude, now we are always familiar with this trick or this method that it is being calculated by the formula which is given by W is equal to M multiplied by G. And whenever we are talking about magnitudes, we don't place the vector, so we drop down the vector. Now M is given by 250 grams, and knowing that the grams is not the SI unit of mass, in order to convert from grams to kilograms we divide by 1000, then 250 divided by 1000, this is equal to 0.25 kilograms. So it is 0.25 multiplied by 10, which is equal to 2.5 newtons. So this is the value of W, and mainly The magnitude changes only for the weight from problem to problem, and all other properties remain unchanged. Now, as for the properties of N, we also have the point of application, line of action, direction, and the magnitude. Now, because N is a contact force, it will be the point of contact. And because it's normal reaction, it will be perpendicular to the support. Now, the point of contact in this case is given by M. Now, perpendicular to the support, this is perpendicular to the support, which is the vertical. Now, because this is downward, then this will be completely upward. And because it wants to balance the effect of W. And because they are telling me they have the same magnitude, for this reason we have calculated the weight at the beginning, and here we are calculating, so we will deduce that N is equal to 25 newtons, which is equal to the magnitude of the weight. Now what is left in number 4 is to represent the above forces using a scale. 1 centimeter corresponds to 1.25 newtons. So sorry, this is 2.5. Knowing that each 1 centimeter corresponds to 2.5 newtons, and by represent it means that we need to draw, and by in order to draw we need to determine the length of these vectors. First of all, in order to redraw, we need to consider the solid S. No need to draw the table again, it's just enough to represent the solid. So this is the point G, and this is the point M. Now let's start by representing the weight, knowing that the weight have the following properties. In order to represent it, we need to determine the length from this magnitude, and this can be done using the scale. The scale is given by 1 centimeter corresponds to 1.25 newtons. From here, so if 1 centimeter corresponds to 1.25 newtons, what about 2.5? It corresponds to which length? So now if you crisscross, you find that 2.5 multiplied by 1 divided by 1.25, this is equal to 2 centimeters. Centimeter because it is under centimeters. So this is the weight having the point of application G, which is vertically downward like this. The length of this vector is given by 2 centimeters, corresponding to 2.5 newtons, acting vertically downward at the point G, and the name of this vector is W. Now we need to represent the normal reaction, which is N, knowing that it has a point of application M. So we will draw it from the point M here, vertically upward. What about the length? 2.5 newtons, it's the same here, so it will be of the same length. So it is exactly like this. Okay. So let me change the dimension of the box. Okay. So this vector is the vector n, 2 centimeters worth 2.5 newtons. And here it's important that n must be represented from the point M, W must be represented from the point G. Now here, because I have changed, let me do a clearer drawing of this. Let me consider another box, which is a smaller box, like this. Okay. This is the point G. This is the point M. This is the weight vertically downward like this. This is the normal reaction vertically upward like this. This is 2 centimeters worth 2.5 newtons. And this is 2 centimeters worth 2.5 newtons. Okay. So that's it for me in this video, guys. In the next part, we'll complete solving exercises on these chapters.